Okay.
Okay, so let me say again that we have Teng from the Institute of Theoretical Physics, who will tell us about magnetotransport and complexity of holographic metal-insulator transitions. Please go ahead when you want.
Okay. Thank you for your introduction. Hello, everyone. My name is Teng, and I come from Institute of Theoretical Physics, Chinese Academy of Sciences. My topic today is magnetotransport and the complexity of holographic metal-insulator transitions. Firstly, I will introduce the background. A good metal and a good insulator are totally different systems. So the mechanism of metal insulator transition is one of the least understood problems. Many theories have tried to understand this phenomenon, and lots of them made a big success. In the spirit of effective field theory, a holographic model of disorder-driven metal insulator transition was proposed, although there are some issues haven't been understood well. Given the rich phenomenological features of this setup, it is worth understanding the theory further and uncovering some generic features. This is the holographic model we use, where kappa n is a gravitational constant, and E stands for U1 charge. Capital Y and capital V are functions of translation breaking sector X, and X takes this form. Because of consistency of the theory, there are some constraints on the couplings. This is the constraints. As we will see later, the derivative of Y, which should be negative, plays a key role in triggering metal insulator transition. According to variational principle, we can obtain the background solutions. This is the background solutions. Notice that this model admits asymptotically ADS black-brane solution. Gauge field takes this form, where rho and B are the charge density and the magnetic field, respectively. Alpha here represents momentum dissipation, and it also represents the resistance of a material to electric current. The larger alpha is, the larger the resistivity is. The alpha is called disorder strength. In the presence of magnetic field, DC conductivity is described by a two-dimensional matrix, and resistivity is described by a two-dimensional matrix too. This is conductivity, and this is resistivity. If we consider clean limit, it means alpha goes to 0. Then we can parameterize the coupling Y and V by this form without losing generality. K is a parameter, and it should be positive because of the constraints of function Y. At the 0th order, it means when alpha equals to 0, we immediately obtain these two equations. Notice that these two results are independent of temperature and the details of the theory we are considering. This universal feature can be understood as a generic consequence of Lorentz invariant when alpha goes to 0. Note also that the conductivities do not divergent in the clean limit. This is due to the Lorentz force on the system, which will violate momentum conservation. After clean limit, we will consider a leading correction coming from dissipation. Then we can obtain conductivity of x direction and the temperature by expanding small alpha. Requiring the conductivity and the temperature shouldn't be negative, we obtain these two equations. Given a positive temperature, the conductivity should also be positive. This allows for this relation. For general choice of B and rho, we finally obtain the constraint of parameter K. This is the constraints. From now on, we give a generic constraint on Y without referring to the nonlinear details of the coupling functions. Next, I will introduce metal-insulator transition and scaling behavior. At first, we must emphasize the definition of metal and insulator. This kind of definition has been frequently used in the field of condensed matter physics. When considering high temperature limit, the resistivity can be written in this form. This equation tells us y derivative of y must be smaller than 0 plays a key role on triggering metal-insulator transition. In order to see that, we can turn off magnetic field first. Only if K is positive, the coefficient of temperature term could change sign. Once K is negative, the coefficient of temperature term are always negative. There is no metal-insulator transition anymore. Now we define a critical charge density ρC like this. When rho is smaller than ρC, the resistivity decreases with temperature increased. The material displays insulating behavior now. On the other hand, rho is bigger than ρC. The material displays metallic behavior. The former is the insulating behavior, sorry. This means charge density could trigger metal-insulator transition. Actually, metal-insulator transition can be also triggered by magnetic field and disorder strength. Recalling the expression of the resistivity, it scales with a single parameter T0. Here, plus represents insulator and minus sign represents metal. T0 is a function of alpha, rho, and B. The Rx of T curves for different rho can be made to overlap by T0 along T-axis, yielding a collapse of the data onto two curves. An insulating behavior for rho smaller than ρC and a metallic behavior for rho larger than ρC. Near metal-insulator transition, T0 can be written by this form where C is independent of rho. We can see that the metallic and insulating curves are mirror symmetry by this relation. This means the mechanism responsible for transport in insulating and metallic phases are related. This figure shows the collapse of resistivity data into two separated holes for broad interval temperatures. Here we consider linear model, which takes this form. On the left, it is the relation between resistivity and temperature at different charge density rho. It is clear that they are totally different curves, but they can be made to overlap by T0 along T-axis, as shown on the right. All of metallic behavior curves gathered together, and the same with insulating behavior curves. This is the scaling behavior by changing charge density rho. Then this figure shows the collapse of resistivity data into two separated holes for broad interval temperatures. Here we also consider linear model, which takes this form. On the left, it is the relation between resistivity and temperature at different magnetic field. It is clear that they are totally different curves, but they can be made to overlap by T0 along T-axis, as shown on the right. All of metallic behavior curves gathered together, and the same with insulating behavior curves. This is the scaling behavior by changing magnetic field. This slide shows the collapse of resistivity data into two separated Horsfall broad interval temperatures. Here we also can see the linear model which takes this form. On the left, it is the relation between resistivity and temperature at different disorder strength alpha. It is clear that they are totally different curves, but they can be made to overlap by T0 along T-axis as shown on the left, on the right. All of metallic behavior curves gathered together, and the same with insulating behavior curves. This is the scaling behavior by changing disorder strength alpha. According to those three figures, we can see that the metal-insulator transition can be induced by charge density, magnetic field, and disorder strength. The collapse of resistivity data into two separated Horsfall broad interval temperatures. Actually, our holographic results agree with the experimental observation in some two-dimensional samples and materials. This figure in this paper gives an example. After discussing scaling behavior, now I will introduce phase diagram. This figure shows conductivity with respect to disorder alpha and temperature. It can be divided into four regions, so-called good metal, incoherent metal, bad insulator, and good insulator. These dashed lines represent boundary of two different phases. We can distinguish them apparently by plotting optical conductivity with respect to frequency. A good metal is the red line. It shows a Joule behavior which has a Joule peak at low frequency, while an incoherent metal doesn't have. Incoherent metal is the green line. Insulator has a small conductivity at low frequency. The difference between good insulator and bad insulator is how small the conductivity is. Here, the blue line is bad insulator and the purple line represents good insulator. Notice that all phases share the same symmetries of the underlying theory. This is beyond a simple Ginsburg-Landau description. Now the question is there any other probe that is able to characterize different phases? To find this kind of quantity, we plot specific heat, charge susceptibility, and complexity respect to alpha and temperature, as these three figures shown. But unfortunately, they couldn't describe different phases. Now I will make a conclusion. We consider a holographic model like this. First, we propose a generic constraint on function y without referring to the nonlinear details of the coupling functions. Then we discuss the holographic metal-insulator transition induced by charge density, magnetic field, and disorder strength. Universal scaling behavior is uncovered, which agrees with the experimental observation in some two-dimensional samples and materials. At last, here are some open questions after our work. Because we focus on the simplest homogeneous background, it is possible to extend our studies to more complicated holographic systems, which break translations without retaining the homogeneity of the background. So far, we limited ourselves to the electric conductivity. It is also worth studying thermal response and mechanical response. Despite a lot of work on this model and generalizations, the physical nature of the dual field theories is still not well understood, and so on. That's all. Thank you for your listening.
Thanks, Jay, for your talk. We have plenty of time for questions or comments. Please go ahead. Also, I didn't say it before, but let me just emphasize that people can just ask questions whenever you want. Just unmute yourselves. Any questions? So can I ask you, in the end, you didn't talk much about complexity, so there was nothing interesting, or you showed just one plot?
Do you mean the
and what did you mean by, what do you mean exactly by complexity of formation? What did you compute there?
Actually, the complexity part is done by my colleague. So I only just can say sorry sorry, what's on me?
No problem, don't worry. Okay. So I might have another small question. So you talked about insulators, but of course, at least I think in all the plots you showed, the conductivity was never vanishing. Can you get the conductivity to vanish like in most of the... I know we normally call insulators if just the resistivity has the right slope, but can you make it vanish or in these models?
Sorry,
vanish the conductivity or make the resistivity infinite? I mean, in principle, an insulator, right, as you go to 0T, shouldn't conduct at all. Do you have any comment on that? Yeah, for instance, like this, can you make the purple line really goes to 0 instead of finite at 0?
Do you mean the dashed lines?
I mean, for instance, the DC. So in the plots, in the plot you have in the bottom, you can see the AC resistivity, right? Conductivity. So
yeah, this is DC conductivity and
okay,
this is AC conductivity.
Okay, maybe, yeah. So maybe you're saying that in the color in the density plot is really the resistivity 0 at if I go to the probably the lower right corner, or is it always going to have a remaining conductivity?
If we go to lower, sorry, because my spoken English is poor. Actually, this talk I prepared a long time, so maybe I can't understand you. Sorry.
No, bro, it's my fault. Okay, don't worry. Let's see if we have any more questions. And if not, I guess we will wait, because next talk is, yeah, we'll have half an hour. So if there's no more questions, I will leave this open. So there can still be questions or comments. I will stop recording. Where is the recording? Here.